this video I'll be talking about McCulloch-Pitts neuron. So if this is a neuron and like there are like n inputs for this neuron, okay, so let's assume this all the inputs are Boolean variable as for now, and also the output is like Boolean variable. Okay, so this neuron can be divided into two subsections. So first one is aggregator. Okay, so this one is like aggregator, which aggregates all those inputs. I mean it's just a sum. It will do just a summation of those inputs, right? And next one is like deciding function, which will take a decision. Like it will take the decision based on the aggregation of those input. Okay, and it will decide whether to fire or not this neuron. Okay, so now let's see the mathematical framework for this model. Framework. Okay, so this g is the function. G is the function of all those inputs, and it's nothing other than just summation of all those inputs. Okay, so in a compact form we can write it as like I'll be ranging from 1 to n and just summation of x. Okay, then this y will be the function. I mean y is like this 0 is like if the neuron fire, then the y will be 1, and then if it doesn't fire, then the y will be output will be 0, right? Okay, this firing will be decided by this function f, which is again a function of gx. Okay, so overall the y will be either 1 or 0, so firing of the neuron or not. So this neuron will fire if the summation of all the xi is greater than or equals to some threshold value. Okay, and if it doesn't fire if this summation of the sum of all those inputs is less than the threshold value. Okay, so this is a threshold value which will be hand coded for this McCulloch-Pitts neuron. So in order to make this neuron work for different purpose, we have to hand code this hyperparameter. Okay, so this is the only hyperparameter that we have to learn for McCulloch-Pitts neuron. Okay, let's see some examples. Okay, so now so we'll assume this McCulloch-Pitts neuron with only two input, x1 and x2. Okay, so g, f, and then y will be either 0 or 1. Okay, so there is some hyperparameter theta which we have to like hand code it for different purpose. Like if we want to do for AND gate, then this both the input should be 1, so that the summation of so let's say g of x. Okay, x is again, okay, so x is a vector of x1 and x2. Okay, and this has to be like x1 plus x. Okay, so let's make, okay, so this is a summation and we have only two inputs, and this is like x1 plus x2. Okay, so for this both for AND gate, this both x1 and x2 input has to be 1, otherwise this neuron won't fire. So the sum, like if both the inputs are 1, then the summation will be 2, and for this neuron to fire, this has to be greater than 2, because here we have like this symbol, right, greater than. Even if we like substitute like the values of 1 for the both inputs, then that will be 2, but looking at this equation, that has to be greater than 2. Okay, and then only this neuron will fire for the AND gate. With like that neuron will work as a AND function. Okay, so if we want to like if we want that neuron to act as a OR gate, then the summation of xi Okay, I'm writing it, rewriting it. Then for this OR gate, either this input has to be 1. So either one of these inputs should be 1. So it can be both 1 or either one of these 1. So that means it has to be like greater than 1. Okay, so now let's see the graphical let's see the graphical representation of those gates. Graphical reasoning, or let's say reasoning. Okay, I mean, like, exactly how, what does that mean? Like, just we want to see it in a graphical way. Okay, so let's first do it for OR gate. Okay, so if this is 0 0 0 1, oh sorry, okay, so this is 1 0, okay, and this is 0 1, and here is 1 1. Okay, so what does this mean? Like, for OR gate, this has to be greater than 1. So like, if we want to get one single linear equation, so that's like x1 plus x2 is equal to 1, right? So this is the minimum line that needs to be fulfilled for the AND gate. So this line is nothing other than this, passing through these 2 points. Okay, so this is x1 plus x2 equals to 1. So for our so from this equation, what you can find is like x1 and x2 should be greater than 1. Then only in that regard, in that cases, this our neuron will fire. So that firing means like our output will be 1, right? Okay, so greater than belongs to this section. So this is like x1 plus x2 should be greater than 1. Okay, so this part, so this is the section where our output will be 1. Okay, and this is the section with y, okay, sorry, x1 plus x2 should be is smaller than 1. So, and this is the section where our output will be, our neuron will not fire. Okay, so in a nutshell, this we are like, through this threshold value, what we are trying to learn is like, we are making this like this neuron is trying to predict this decision boundary. I mean, this neuron is learning this decision boundary, so as to work as a OR gate. Okay, now let's see with for the AND gate or AND function. Okay, so this is like 0 0 1 0 0 1 and 1 1. Okay, 1 1. Okay, fine. Okay, so like for AND function, we have this equation like x1 plus x2 should be greater than 2. So so the linear equation will be x1 plus x2 equals to 2. So this line passes through this point. So this will be this. Okay, so this line is x1 plus x2 is equals to 2. And this is the reason where our x1 plus x2 is greater than 2. Okay, and this is the reason where our x1 plus x2 is smaller than 2. Okay, so this is the reason where our neuron will fire. So that is like our output will be 1. Okay, so let's make it a little bit clear. Okay, so this is like y equals to 1 over here, and this is the reason where our neuron won't fire. So that's like our output will be 0. Okay, so again, So by hand coding this threshold of this 2, what we are trying to do is we have learned this decision boundary for the AND gate.